Okay, good morning, everyone. So we are continuing with chapter 6, which is on uniform circular motion, right? We saw like several examples on uniform circular motion, which was a car on a flat road ataupun a car moving in a circular motion, but it was on a flat road, macam roundabout lah, like a roundabout. So in this situation, this is our car, by the way. In this situation, we know that there is some friction acting towards the center, and this friction will be equal to centripetal force. Centripetal force, eh? Yeah. This is going to be equal to centripetal force. And centripetal force, the equation is given by MA, but in this case, the A is special. It's called AC, or centripetal acceleration. So it's just a regular F equals to MA. But in this case, because this guy is centripetal acceleration, therefore the acceleration is also going to be centripetal. And the direction of centripetal force is always towards the center, just like this friction. Now, I equate these two guys together because this is the only thing acting towards the center. How do I know which force becomes the centripetal force? Basically, your FC will become whatever that is in your radial direction, net in the FR. For example, I have, what else? We haven't gone through the roller coaster yet. We talked about a pendulum, right? Talked about a pendulum, and this guy was swinging in a circle. And this is the circle motion. This is the circular motion that is going through, right? So the center of this circle is here. It's not going to be up here, it's down here. Walaupun macam pelik, tapi it's there. So what is acting towards the center will become whatever that is acting towards the center of the circular path is going to be FC, or is going to be AC. Dua-dua boleh. You can write both because FC is equal to MAC. So whatever that is acting towards the center is going to be FC. Now this is where our job comes in. Kita kena identify what is actually acting in the radial direction or what is acting in net in the FR. So for kita dah go through this example and we knew that for a string we would have tension. We are assuming this guy doesn't have mass. Kita assume macam tu ke? Okay, kita bolehlah cakap dia ada mass, tak kisah pun. So mg_t. So the only thing that has a component towards the center of this circular path would be t. If I knew the angle over here, this would become t cosine theta. Or if you knew the angle over here, you can say this is t sine theta. Whatever that works to find out the component of the force acting towards the center. So it's just like our free body diagram, but now you just have to identify what is acting towards the center of the circular path. Okay, sama je macam free body diagram. Cuma kita identify apa yang berlaku kat the center of the circle. Now, what happens if we have another force at the back? Terbalik. Instead of going towards the center, it is the opposite way. So this is where our equation net in the FR comes in. So if you have multiple forces in this direction, satu towards the center, satu away from the center, so your equation becomes T cosine theta. And let's say this is like F random, tak nak cakap FR. F1, kita cakap F1. This is like the random force tiba-tiba dia. So T cosine theta minus F1. So here, I'm actually defining a convention. I'm defining that whatever goes towards the center is positive and whatever is away from the center of the circular path is going to be negative. Sama macam kita define up is positive, down is negative, to the right is positive, to the left is negative. But in this case, is whatever that is going towards the center of the circular path is positive, and whatever that is away from the center of the circular path is going to be negative. So that is your convention. And again, don't have to panic. It's just regular free body diagram. You just have to resolve whatever that goes into the center. Okay, so that is your net in the FR. We also talked about angular speed, which was omega. The speed is omega, and it is delta theta, the change in angle or the change in radius over the change in time. However, the units for this would be radians per second. So this is like, I would say this is the SI unit lah. Okay, radians per second. But the equation is delta theta. Theta can be radians or theta can be degrees. But in this case, please find it in radians lah. Okay, so angular momentum, angular speed or angular velocity or rotational speed is different than your linear speed. This is your linear speed. It's called velocity. This is called angular speed or angular velocity. Kita panggil speed je lah. Angular speed, and this is linear speed. Okay, what is the difference between the two? This guy tells us the speed when we're going in one axis, x axis or y axis. Bila kita dua ada x and y, kita gabung jadi using Pythagoras, using the equation that we find out the magnitude and then we find out the direction. So this guy tells us x and y punya speed lah, okay? But for omega, it tells us the rotation, how fast, how many rotations can it make in a time? How many rotations can it make in a time? This guy, how many distance can it cover in some time? This guy is change in displacement over the change in time. It is finding out the displacement or the distance that it can cover over time. This one, how many rotations it can cover in some time. So these are the difference, and they can be connected. They have a relationship. Okay, they have a relationship, and it is known as V equals to R omega. Now again, what is R? R is the radius of the circular path. Ni kena ingat, memang kena ingat. V equals to R omega. And another equation that I forgot to mention was MAC is also mv squared over R. So AC is V squared over R. This is also another equation that you need to remember from this chapter. This is what you need to know macam mana nak cari. Ni equation yang kena ingat. Ni kena tahu, kena faham, kena tahu macam mana nak buat. Okay, so these are like the basic things yang kita akan cover untuk chapter ni. Not basic, like the key points. Okay. Alright, so I said I'm going to go over the examples, laju-laju, the examples that we covered last time. Did I miss out anything? Cover. Centripetal always towards the center. So acceleration is also towards the center. Kita dah discover why it is always pointing towards the center. If you don't remember, go back to my video. Panjang sikit cerita itu. This one, V equals to R omega. I think we covered everything. Okay, this one. So you have a complete circle is 2 pi radians. 2 pi is actually in radians. 2 pi radians or 360 degrees. It goes from here to here. It is anti-clockwise. So sama macam 0, 90 degrees, 180 degrees. Kita punya direction from 0, 90 degrees, 180 degrees is anti-clockwise, right? So follow that, it's still the same. So 360 degrees is also equal to 2 pi radians. And we, I forgot about frequency. So we know that period is the time taken for one revolution, right? One revolution, kita cakap pasal IKRI hari tu. So period is the time taken to complete one revolution. So 1 over t or 1 over period tells us frequency, and frequency is typically hertz. Okay, frequency is typically hertz, and we can convert frequency to other units such as CPS and also RPM. This is cycle per second. This is revolution per minute. Ini kena tahu. Ini kena tahu macam mana nak.
Push-up.
B for push-up. Okay. Nah, kita kena tahu macam mana nak convert. Alright, so let's continue with the example. Okay. Okay, so this example, this is a horizontal circle. So it was swinging an aeroplane, right? So ada string. So we know that there is tension over here. Kenapa saya punya pen not working? Okay, this is T, this is T. But we want to know what is acting from the circular path towards the center. So I don't really care about the T acting on this guy, right? I just want to know what is coming from this circular path. So we know that we have tension. So tension will be our FC and we can equate it to mv squared over r. Sama juga kat sini, we have tension over here. We have tension over here, acting here. This is also tension. So you have to resolve to know what is acting towards the center. So this becomes, if this is theta, this is theta. So this becomes T sine theta. So T sine theta will be mv squared over r. Kejap kan? Bisa, let's go. Don't make noise. Yeah, don't make noise. Fine. Okay. Okay, and then for this guy, friction was acting towards the center. Yang ni mg, kita lukislah free body diagram dia jap. Kenapa saya punya pen hari ni macam tak okay. mg, we have r, friction, reaction force or normal force. And this is our friction. And these are the only forces that we have. This is new. This is new. You guys have to be aware of this. When this car is moving in a circular path, there will be friction acting towards the center untuk macam kira macam cangkuk dia lah to have that curve motion. Kalau tak ada benda yang tahan dia towards the center, it would just go straight. So it needs that friction to move in a circular path. So imagine like you are going through, you are driving a car. Don't know if you guys have ever drove a car. It's okay. So imagine that you're driving a car and kena lalu selekoh, right? Kena lalu selekoh. What do? You have to like brake a little bit, right? Kenapa nak brake? Sebab nak kena pusing sikit. Sama kat sini, kita nak buat pusingan tu, we need that extra grip somewhere so that we can rotate our path. We can rotate the car punya path. Okay, so it works like that. And also another example that I can think of is jangka lukis lah. We already discussed that one as well. Okay. Okay, so we talked about this. And in this case, this is mu r. We have to solve for r. We know that r is equal to mg. So this is just friction lah. Friction is equal to mv squared over r. Now this is positive because this guy is acting towards the center. If it is the other way, then it would be a negative. Kita always define macam tu. This is the easiest way untuk define the conventions lah. I would say moving towards the center is going to be positive. Of course, that is my convention ni benda yang boleh berubah-ubah kan. Kalau saya nak buat cakap ke kiri positif pun boleh. Saya nak cakap ke bawah positif pun boleh. Sama juga kat sini. I can also say away from the center of the circle is a positive. I can say that. But it means that I have to be consistent when I'm solving the problem. Kalau keluar dari bulatan positif, semua yang keluar dari bulatan going to be positive. And gonna follow lah, okay? But the preferred convention is always towards the center will be a positive. Just like going upwards is positive, going to the right is positive. That is the preferred convention. Okay, so have we talked about this one? I think we have, but saya akan go through lagi lah. So this is a car and it's moving in a racetrack. I don't know what it's called. Tapi benda ni ada angle as you can see here. So the trick to this question is that people usually say that the center of the circle is here, down here. So an FC is this way. That's not right. the circular path, the guy completes a circular path mid-air dekat tengah-tengah bank ni kan. So the center of the circle should be suspended over here, atas, not on the ground. So to know what is the FC or the centripetal force, we have to resolve whatever that is acting this way, not this way. This is wrong. Always identify your circular path first. Find out the center, that is your FC. Okay, that's the tip. So here kita dah we know that this is R, which is reaction force or normal force. This is mg, and we want to know what is acting in the radial direction. And in this case, mg does not have any contribution sebab dia 90 degrees. Anything that is 90 degrees, kita tak payah resolve into components. Sama macam X dengan Y, kalau saya ada force dekat sini, saya akan abaikan untuk letak dalam X. Sebab F1 does not have any component in the X. 90 degrees. Memang tak ada component. It's just Fy, F1Y. There's no X component. Sama juga kat sini, if it is 90 degrees to the radial direction, there's no component. You don't have to resolve it. But if you want, you can. But you will get 0. Okay? Okay, moving on. I hope everyone is okay with this one. Okay, moving on to vertical circle. Tadi kita cakap pasal horizontal. Semua horizontal. Aeroplane, pendulum, it was all horizontal. The car on the bank, horizontal circle. Semua horizontal. Now we're talking about vertical circle. Vertical circle ni I would say is a little bit tricky untuk cover But that's okay, kita akan belajar. So this is a Ferris wheel. And if you didn't know, Ferris wheel also acts using centripetal acceleration. And where is our centripetal acceleration? It is also towards the center of the circle. Circular path is here. Center is here. This way is your FC. Okay, FC or AC. Now here we have like several forces. We have reaction force. This guy is sitting on the seat. Kalau kita naik Ferris wheel, kita kena duduk kan. Tak adalah tergantung tiba-tiba kan. Kena duduk dalam kotak tu, baru dia gerak, macam tu kan. So we have to sit. And when we sit, we have reaction force or normal force. So this normal force is R. This normal force is called R. And we also have our weight acting downwards, which is mg. Now the question is, what is our centripetal force? Sama juga macam horizontal cases. We just write what is net in the FR. Use your free body diagram. We already have it here. So going towards the center of the circle is mg, positive. And going away from the circle is negative mg. Okay, sorry, I forgot. Before we start writing our free body diagram, we need to write our condition, which is MAC. Macam mana saya tahu condition dia MAC? This guy is moving in a circular path. What else can it be? It's not going to be at rest, it's moving. So the only thing left is MAC lah. Kalau MA sahaja, it's going to have a linear motion or like an angled motion. Macam ada angle, and tapi tetap linear. But in this case, we know that it's moving in a circular path. My condition is MAC. Okay, so this one, kita dah tahu condition. Next, what is acting towards the center? Positive mg minus r. So this is what you have. So mg minus r is equal to MAC or mv squared over r. Now in this case, this solvekan for r. So kita try to rearrange this, okay? So mg minus r equals to mv squared over r. This is not capital R, it's small r. This is radius r. So we want to rearrange this. So r becomes mg minus mv squared over r. And here it's saying that positive r we can only obtain a positive r if mg is greater than mv squared over r. When mg is greater than mv squared over r, baru kita punya r positive kan? So since we have these two things sama, it's just saying you have to have gravity to be greater than b squared over r, or b squared over r needs to be smaller than gravity. Sebab gravity kita tak boleh tukar kan, gravity is constant. So we need to have a velocity that is less than g for us to have our normal force. What happens when you don't have normal force? What happens? Any guesses? Salah tak apa? What happens if we don't have normal force? Why is it important for us to find positive R?
Jatuh.
Jatuh, betul. Melayang lah. Jadi tak selamat lah Ferris wheel ni. Korang terbabas eh. So you need that reaction force to maintain that contact between your butt and the seat. If it's not in contact, you know that you're like in a bad situation lah. Okay, so this is what we don't want. So always the velocity of this Ferris wheel, if you notice, it's not that fast because of that reason. If it goes too fast, accidents will happen. So the velocity of this guy or the Ferris wheel has to be less than gravity. Gravity ni kena lagi besar lah, okay, daripada v squared over r. And radius pun memainkan peranan juga. Okay. What else? So this is why we are trying to solve for r positive. So can r be 0? Yes, it can be 0. It just means that your butt is no longer touching the seat. Can r be negative? Can our r be negative? Is it possible? Boleh tak r jadi negative?
No.
Boleh kan? It's just going to be 0 or positive. Either you have it or you don't have it. Okay. So now it's asking us, try to solve for r at the lowest point. Okay, so let's see. So at the lowest point, this is our highest point. This is the highest point. Dah ada tulis kat sini dah, tak apalah. Okay, so kita akan grupkan macam ni. Okay, at the lowest point, FC is equal to RMG. Let's figure out how they got this. So at this point, we are here. We need to know what is the maximum or minimum speed to maintain contact with the seat. So net in the FR. So here our R is acting towards the center. Terbalik. Tadi MG acting towards the center. So MG jadi positive. In this case, R is acting towards the center. Walaupun direction diorang tak sama, but this guy is acting towards the center. So this R is going to be positive. And our MG is going to be negative. Now remember, our positive is always towards the center. Anything that is away is going to be negative. Okay, so I forgot again to write the condition. Let's write that. MAC, and this is R minus mg. So I want to rearrange this to solve for r. Okay, I want to rearrange this to solve for r. So r is going to be MAC plus mg, or mv squared over r plus mg. And r is always positive in this case. You always have your weight, right? Because we are on Earth. You always have your weight, so r is always going to be positive, and mv squared depends on your speed. So you can go as fast as you want down here. You can go as fast as you want down here. It doesn't matter because you're still going to maintain that contact. Tapi bila ke atas ni, tak boleh laju. Kalau laju, melayang kita punya customer. So at the bottom part of the Ferris wheel, we can have whatever velocity that we want and still maintain contact. And at the top, it's going to move slower because we want to maintain contact and we don't want to kill ourselves. Okay. So if you notice, if you ever have naik Ferris wheel, you would feel that kat bawah ni kan, you would feel like extra heavy. I don't know if it's just me, but kalau kita naik Ferris wheel ni, kita rasa kat bawah ni kita rasa macam ada orang tekan-tekan kita, tapi dekat atas ni kita rasa macam ringan, rasa macam almost nak melayang sikit lah, tapi tak melayang. Have you ever experienced that? I don't know if you guys have tried that, the Ferris wheel. So you would feel like you are suspended up here, and kat bawah ni you feel like someone is pushing you down. Now remember, our weight, our perceived weight What is perceived weight? Weight yang kita rasa, benda yang kita rasa. Sekarang ni kita rasa normal je kan. Tapi perceived weight can change if our R is no longer equal to our weight. Sekarang ni perceived weight saya mg. Saya tahu mg, bukan saya tahu. Saya rasa mg tapi sebenarnya saya tak rasa apa-apa. Sekarang ni saya rasa normal. I'm just sitting on a chair. There is mg acting on me. R is equal to mg because I'm not flying. R is equal to mg and my body feels mg and my body is used to mg. Now if R increases beyond mg, I will feel like ada orang tekan-tekan lah. So this is what we feel when we are at the bottom of the Ferris wheel. Our R is no longer mg, but instead it is R equals to mv squared over R plus mg. So ada extra weight tu. So kita akan rasa macam kena tekan. Sama macam kita naik lift. Remember the lift situation? Kita naik, kita rasa macam nak terjatuh, turun rasa macam ada orang tekan. So this is the same concept here. But this one is circular. Okay, so this is what we're dealing with. So if R is equal to mg, we just feel normal. If R is greater than mg, kita rasa macam kena tekan. But if R is less than mg, we would feel like we're like macam nak melayang ataupun macam tengah terbang sikit. Tahulah. This is what I feel lah. Okay. So at the highest point, R positive is only applicable when velocity is less, v squared over R is less than g. Can only go at a slow speed to maintain contact. At the lowest point, R is always positive, so we can go at any speed that we want and our perceived weight will be greater than kalau kita ke atas. Ke atas kita akan rasa ringan, ke bawah kita akan rasa sangat berat. And then we have the roller coaster. Okay, wait, do we have any questions about the Ferris wheel? Semua faham tak what's going on here?
Doktor, nak tanya.
Kalau yang circular motion horizontal ni, kalau kat bahagian kiri dengan kanan tu macam mana dia positif ke atau negatif yang R dengan mg tu kalau kiri dengan kanan position dia?
Okay, so ni Iqbal okay, thank you for the question. Saya lupa nak cover. So this is not a horizontal circle Iqbal, this is a vertical circle sebab vertical lah kan. Kalau horizontal dia macam ni. Okay, so this is a vertical circle.
Salah.
Okay, tak apa, saya bagi tahu semua orang supaya diorang aware. So this is a horizontal circle, this is a vertical circle and Iqbal is asking what happens if our Ferris wheel is on the right or on the left? What happens to R and mg? What is the direction? Now, kita ada one contoh kat sini yang orang dah lukis kat kita. We always have to find out what is acting in towards the center. Now, in this case, would my R have some component towards the center? Yes, the answer is yes because it's not 90 degrees. So, saya boleh cari komponen tu. So, it would become, if this is my, susah nak bayangkan, kejap, kita akan resolve macam ni. So this becomes our R, I don't know what axis we are going to call this. Let's just call this R1 and this is R2. Kita akan resolve R to its components and this will be what is acting towards the center. But in this case, this is going to be negative R2. Okay, you have to resolve it. Kena macam anggap ada XY lah kat sini. Susah pula kan. So you have your component. Okay, we want to know what is acting towards the center. Let me just draw a small circle here. Small arrow. So R, I'm going to resolve it. This is R1 and R2. Terbalik. Let's call this R1 and R2. This is our axis lah. This is the same direction as our radial and this is perpendicular to our radial. This is how you resolve it. So apa lagi? mg kita kena cari dekat this direction and also direction parallel to the radial. So this is going to be mg, mg cosine theta. This one, let's say this angle is over here. This is going to be R2 cosine theta. So my net in the FR is going to be mg cosine theta minus R2 cosine theta, whatever this angle is lah. Okay, this is 1 and this is 2. Okay, so you have to resolve it into its radial component. Kat sini, resolve it into the radial component and also the perpendicular component. Macam XY juga, cuma kita punya parallel direction is now the radial, towards the center. This is our parallel axis. Okay, so how do we relate back to the one that we learned in linear motion? Remember, saya cakap follow your motion. If you are this ball, this is going to be your imaginary axis X. This is going to be your imaginary axis Y. And this is not actually true because X is not this way. X is this way, right? Kita anggap this is our new X and this is our new Y. Sama kat sini. Sama ada juga kat sini. This is our new X and this is our new Y. But in this case, I'm not going to call it X sebab dia akan jadi confusing. I'm just going to say this is acting in the radial direction. So I just want to know what is the forces in this axis. So kena resolve. But if you feel like you understand better by calling it X and Y, you can do that. But not recommended lah, okay? So X and Y. So this is going to be perpendicular to the radial direction. This is going to be parallel to the radial direction. So kita nak tahu yang parallel sahaja. So if you didn't solve for Y, that's fine too. Boleh je kalau faham. Macam saya tak solve pun untuk Y tadi. I just wanted to know what is acting here. And I'm good to go. Okay, so this is unnecessary lah. X and Y ni unnecessary. You just have to resolve it in this direction. Okay, faham ke semua? Macam complicated sikit kan? Tak apa, kita cuba nanti. Kita cuba untuk example lain. So my takeaway point for this slide is depending apa saya nak cakap, wherever you are, either atas ni, kanan, tengah-tengah kat sini ke, bawah ni ke, always find out the forces acting towards the center. It doesn't matter where you are, you just have to find out what is in acting towards here. Okay, so if your R and mg is not in the same direction as your radial direction, this is your radial direction, FR ataupun FC, then you would have to resolve your R and mg into that direction. Okay, so if you notice kan, your Ferris wheel on this right hand side, tak tahulah korang pernah try ke tak, tapi nanti bila you guys find a Ferris wheel, you can try. If you are on the right hand side or on the left hand side of the circular path, you would know that this guy dia akan bergerak-gerak. Dia macam tak stable. Sebab kita punya R ni dengan mg, kalau dia macam vertical saja, tak ada komponen tau kat AC ni. So bila kita gerak-gerak sikit, kita ada angle, kita ada macam force lah yang acting towards AC. So saya perasan kat sini macam memang tak stable tau on the right and on the left. I wouldn't say it's dangerous. It's just that we need to like support the circular motion by moving the Ferris wheel. That's why the Ferris wheel tu dia ada like boleh gerak-gerak lah instead of like fixed. It's not fixed, right? Dia macam boleh, dah lah, dia korang try lah. So this is as much as I can explain. Okay, so try it and try to relate it back to centripetal acceleration. Saya pun baru belajar bila saya ajar korang sebenarnya, because back in degree days, I wasn't interested in physics. Okay, so vertical circle for a roller coaster. So this is much more interesting in my opinion. So roller coaster, instead of Ferris wheel kan kita punya R always like going upwards, right? Kita selalu duduk je and then dia rotate. So that was easy. So what about roller coaster? Roller coaster is like complicated sikit, but interesting. So when you're riding a roller coaster, you know that your head is like macam ni. This is the direction of your reaction force because you are on the seat and kalau terbalik pun terbaliklah kepala kan. So your R keeps on changing. Your R keeps on changing. So it's different than the Ferris wheel. So how do we find out what is acting towards the center? Do I still have time? Yes. So what is acting towards the center? So you would have R component and mg component. So net in the FR is going to be MAC going to be equal to R plus mg. So this is what you are feeling. So mv squared over r. So what are you feeling? R is equal to mv squared over r minus mg. Now, if you notice, when you're going up here, do you go really fast or do you go really slow? Kita go atas ni kita jadi laju ke jadi slow? Ingat tak?
Slow.
Slow ke? Korang
Laju.
kena kepala
Laju.
terbalik kot. Laju kan? Yang slow tu macam ni. Yang bila korang macam ni, biasa kepala korang. Kat sini slow lah. Waktu ni macam, waktu tu slow boleh lah sebab MG bawah ni kan. Kalau nak laju ke slow ke boleh kat sini. This part, bila kita naik slope, kita slow. Tapi bila kita punya kepala terbalik kan? Kalau korang slow, jatuh kot. You can't be slow guys. If you guys have a chance to ride on the roller coaster again after the pandemic, you would notice that you are going really, really fast. Kenapa? Because if you are not going fast enough, if your mv squared over r is not greater than mg, you would fall down. We don't want that. Okay, so engineer dah fikir siap-siap dah, okay, kalau naik atas ni kita punya V kena lagi besar daripada mg sebab kalau tak nanti semua orang jatuh and then will be sued. So they designed it to be fast over here, okay? So it is based on this. R needs to be greater, R is only positive if your mv squared over r is greater than mg. So we can cancel this out sebab dia sama kan? So v squared over r needs to be greater than gravity. Your velocity has to be high here. Okay? And this is at the highest point. You have to go really fast. So at the lowest point pula. At the highest point for positive r, v squared over r needs to be greater than g, needs high speed to not fall off. Okay, what about at lowest point? Lowest point, our head is, I wouldn't say head lah, kita tengah duduk kan, so our normal force is this way, tapi saya selalu fikir kepala je. So our normal force is this way and this is our mg, so net in the fr is r minus mg, forgot the condition, mac. So this is going to be mv squared over r equals to r minus mg. And in this case, your r is going to be equal to mv squared over r plus mg. So at this point, they don't really care if you're going slow or fast. You will always be safe down there. If you don't have, even if you don't have any v, you will still maintain contact, right? So if your v is 0, you're not moving, you're not going to fall off lah, is what I'm trying to say here. R plus mg. So your R is basically just your mg. So if you notice, if kalau roller coaster tu tiba-tiba je berhenti sekejap kan dekat bawah, you wouldn't feel anything. You would just feel normal. Tak ada rasa macam sakit perut ke apa ke, tak ada rasa apa-apa. Rasa normal je sebab R equals to mg. But when it starts to move, laju, if you go really, really fast down here, your R is going to be big. Sorry, your V is going to be big. So mv squared over R is big. Your mg tambah dengan benda yang dah besar ni, you would feel like sakit perut. Rasa macam ada orang tekan-tekan. Macam, you know that feeling in your stomach when you go really fast down a slope. So this is why, because mv squared over r plus mg plus your weight. Kalau rasa weight je tak apa, rasa normal je. Tapi bila lebih daripada weight, kita akan rasa macam kena tekan ataupun sakit perut tu lah. Okay, so that is your vertical circle. Any questions? So everyone's okay with this example? Always find the net in the FR in the radial direction, okay? So this is an application. So we talked about roller coaster, Ferris wheel, pendulum, car on a bank. So this is an actual application in labs that uses centripetal acceleration. So let's say we have like blood, right? Kita punya blood kan ada, this is bio lah. I'm gonna make bad facts. Okay, I'm not gonna use a blood lah. I'm gonna use like a regular suspended sample of water. So I have like this solution, and solution ni dia ada macam suspended particles, but this particle is like super small. But we know that the solution has a different refractive index R1, and the suspended particles have a different refractive index. Maksudnya diorang punya weight, diorang punya property semua lain lah, solution dengan suspended particles ni. So saya nak separatekan diorang, tapi sebabkan suspended particles ni kecil sangat, susah nak filter. So I can't really filter it. So what do? I use centrifugation. What does centrifugation do? Kita letak solution kita dalam ni, kita pusing dia laju-laju, and what would happen is these two things would be separated. They would be separated to become, the suspended particles would be down here and the solution would be up here, or vice versa. Kadang-kadang suspended particles kat atas, solution kat bawah, depending on who is heavier. So dia akan separate based on the properties of the material. Kalau ada different weight, different refractive index, benda tu akan dia akan separate lah. Okay, sebab kenapa? Because these guys move at different speed. So this moves at different speed, this moves at different speed. So when they move at different speed, you can actually separate them. You just have to know that much lah. So an application that uses centripetal acceleration is centrifugation or centrifuge. Panggil dia centrifuge. A centrifuge works by spinning very, very fast. This means that there must be a very large centripetal force. The object A will be pushed to B. Object A, oh yes, this one. This is an object, it will be pushed down here, just like the suspended particle. An application of centrifuge is to separate solids in liquid solution, or in this case, yang selalu orang pakai is blood. So saya tak tahu dia separate apa. Separate platelet ke? Entahlah, benda-benda macam tu lah. Tapi diorang pakai untuk blood selalunya. Saya pakai dalam lab saya untuk separate material. Saya tak pakai untuk blood because I don't do bio. I can't do bio, okay? So that is an application. Okay, next. Electron orbiting the nucleus. Yang ni kita akan belajar next semester. Saya rasa tak apalah, kita hold dulu. Okay, problem solving strategy. Kita try to cover one problem example. Nanti kita habiskan kelas. Okay, so read and understand the question, visualize and sketch. Identify the object in circular motion, sebab kita kena lukis free body diagram dia. Identify all forces acting on the object, weight, normal, friction, tension, if they have any. Sketch the free body diagram of the object. For forces in 2D, the best choice of axes are along the radius and tangential to the circular path. Okay, so this is the axis that they are using. So soalan yang Ferris wheel tadi tu, dorang panggil ni tangential axis. That's much better than XY. This is tangential axis and this is along the radius. Radial je lah, radial axis. Okay, so instead of X and Y, you can call this tangential or radial. And kalau kat bawah sini, tangential, radial, acting towards the center, right? Tangential, radial. Radial always in the direction of the circle. Tangential adalah perpendicular to that direction. Tangential, radial. So T, R. This is T, R. This is R, T. And this is R and T. So apa-apa yang dalam direction center of circle, that is your R. Perpendicular to that is your tangential axis. You can define it like that if it helps. Okay. Oh, kat sini they define F net in the radial is mv squared over r, which is MAC. And dia dah declare siap-siap net in the F tangential is equal to 0. But we don't really care about that. Okay. Moving on. State your final answer. Do not forget units. Okay. Example 6.1. Let's just cover one and then we are done for today. A child of mass 25 kilogram sitting 1.1 meter away from the center of a merry-go-round. So this is a merry-go-round. moves with a speed of 1.25. So this is the linear speed. Macam mana saya tahu linear? Sebab dia cakap meter per second. Kalau angular speed, it would give me something in radians per second, right? So this is our linear speed. Calculate the centripetal acceleration of the child. So I have V. How do I find AC? So kita dah tahu V is AC is equal to V squared over R. So I just substitute that. V is 1.25 squared over radius. Radius is 1.1. So that is my AC. And this is meter per second squared. And this is meter. So this would be meter squared per second squared over m. Cancels out. So you are left with meter per second squared, which is acceleration. Just the normal stuff here, nothing new. So AC is 1.42 meter per second. The net horizontal force exerted on the child is MAC. So if we know the mass, we just multiply with AC. The end. Okay, ni esok pula, next week, okay? Kita akan habiskan examples on circular motion. Ada a few kat sini. I want us to really focus on this one, so I don't want to do it today. And then kita akan masuk gravitational force. Okay, so that is it for our class today. I hope you guys have a great rest of the day. Take care of yourself and don't forget to have your lunch later on or breakfast. Bye, guys.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Bye.
Thank you, Doctor.
Bye.